Good morning, student. This is our third lecture. So now we are going to discuss the electron density in the bulk materials. Already we have discussed about the electron density in the bulk material. You know how to solve the time independent Schrödinger equation for the electron inside the metals. So using that Schrödinger wave equation, we will get the energy eigenvalue. That value En is equal to the energy of the electron inside the metal cubical box, that should be equal to nx square plus ny square plus nz square into the Planck reduced Planck constant square h cut square pi square divided by the 2ml square. This is the allowed energy of the electron inside the metal. Here nx, ny, nz represents the quantum numbers, the allowed quantum number of the electron. But this is not equal to 0, but it can be equal to from 1 to infinity. You can use uh, any value for nx, ny, z. You can calculate what is the energy of the electron, the allowed energy of the electron inside the metal. Suppose if you are considering the value for the nx, ny, nz, these values are equal to 1 comma 1 comma 1, then the energy of the electron E nx1 ny1 nz1, that should be equal to nx square is 1 square, that is so here ny also 1 square, nz is also 1 square, 1 plus 1 plus 1, it is 3 times the h cut square pi square divided by 2m L square. This energy of the electron for the three quantum numbers 1, 1, 1. This is the ground state energy because this is the minimum allowed energy for the electron inside the metal. Suppose the next higher number you can choose for nx, ny, nz is the next number. You can choose 1, 1, 2 or 1, the nx is 1, ny is 2, nz is 1, or you can choose nx is 2, ny, nz are 1, 1. These are the three states for the electron. The That means the wave function for the electron is different for the next energy state, but the energy is same. Even if you are substituting n, ny, ns at this value or this value or this value, you will get the same energy level. That means suppose if I am choosing E211, that will be equal to the energy for the second state is E121, that should be equal to E112. That energy is equal to, if you are substituting that value nx 2 square ny 1 square plus nz 1 square, it will give like a 4 plus 1 plus 1 times that value, the Planck constant, reduced Planck constant square, the pi square divided by the 2m, the length of the material, that is square. So that value is equal to 6 h cut square pi square divided by 2 em L square. So the energy for these three states, that means the states of the electrons are different, but energy is the same. This is called, we can call this is an degeneracy for those electrons. That means three different states but the same energy. This is called the degenerate states. So this energy is called the degenerate energy. Now you can write the n square in general, that should be equal to nx square plus ny square plus nz square. That means the n small n is equal to square root of nx square plus ny square plus nz square. Now we want to compute the number of allowed energy states inside the metals, or the number of allowed electron in the particular energy level inside the metal. How we have to do that one? because already we have told the nx, ny, nz are positive integers, so you can assign the any value. Why it is positive integer? That is the one question you can ask. Why it's positive integers? So because if you are looking at that energy, the energy expression, that should be equal to the nx square, ny square, nz square. So if you, even if you are substituting the negative value for the nx, ny, nz, it will give the positive value. That means whether if you are computing using the negative integer or positive integer, you are counting the same energy level. So you can choose the positive value for nx, ny, nz. So now what you want to do, you can draw the energy sphere, that means the number of allowed energy state for the electron inside the metal. How you got to do means, just you need to draw the three axes. Each axis represents the by the quantum number, the first nz, nx, ny. Then you can put the values for the nx, ny, nz. Then you can compute the point inside the sphere. Suppose if I am choosing the first point is 111, that means all the three quantum numbers having the 111, that represent the ground state. But you can ask one question: how many electrons allowed in that states? According to the Pauli exclusion principle, this energy states is occupied by the two electron. One is the upspin electron, another one is the downspin electron. So in this particular energy, now you can assign the next number for nx, ny, ns, 112 or 211. Suppose 211 represent this point, then the next point 121 represent this point, the next point the 112 represent this point. This is the next allowed energy state for the electron. In this 3 point can occupy by the 2 electron, that means 6 electron can occupy, but these energies are same, that is called degeneracy. Already we have discussed. Now you can ask one question: what is the distance between these 2 points? The distance between these 2 points in the energy space is 2 pi pi l. So now you can make the smallest cube in this energy sphere. What is the volume of the cube? The number of states is allowed inside the cube means, only because the in the simple cubic structure only one atom is allowed. That means the, if you are thinking this is a simple cubic, only one state is allowed. What is the volume of the state means 2 pi pi l whole cube. But up to how long you can assign the point, or you can fill up the electron means up to the maximum energy, that means up to the Fermi energy. You can assign the all the points, then you can compute the all the electron. So that means up to this radius. So you can call this is the maximum allowed energy for the electron. The of the radius is the n. What is the radius here? Already I wrote the radius n here. It should be equal to nx square plus ny square plus nz square. This is the radius of the sphere. That means the allowed energy for the electronic states in the metal. So how you can compute the allowed energy of the electron means, first we need to calculate the total volume of the sphere. The total volume of the sphere is simply is equal to 4 pi 3 pi r cube. Here radius is n cube. But this is the total volume. But we are going to take the only the positive values of the x. That means you are going to calculate the first atom. What is the volume of the first atom is 1 by 8 of the first. So only we are calculating the positive values of the quantity. That means the first atom. The volume of the first atom is 1 by 8 4 by 3 pi n cube. So what is the smallest volume? The allowed volume, that means single state volume, is it's simply 2 pi pi l whole cube. So this is the total volume. This is the smallest volume. If you are dividing these two, it will give the number of allowed states for the electron. So the number of allowed states. So number of states, how many states you can calculate, that should be equal to, so the volume 1 by 8, 4 by 3 by the radius cube. This is the total volume divided by the volume of the single state. So once if you are dividing these two, it will give the number of allowed states for the electron. But I want to calculate the number of allowed electron in this state. That means each state is occupied by the 2 electron. That means you need to multiply the total states by 2. So if you multiply by 2, it will give this is 4. The numerator is 4 pi n cube by 24. The denominator is simply L cube is V divided by 8 pi cube. So now if you want to cancel some of the quantity, you can cancel. Here 2 4s are 8, you can cancel this 2. Here 1 pi you can cancel. The final quantity you will get n cube. The volume of the cubical box by 24, it will be pi square. This many number of electron is allowed inside the metal box. So next thing we want to compute the density of states, the electron density in the bulk material. That's the thing we are going to do in the next. We know that the energy of the electron E equal to n square, h cut square, pi square divided by 2ml square. So you can rearrange it and then get back that value for n. That should be equal to 2me divided by h cut square, pi square, L square whole power of. This is a quantum number. Already we have done it. The number of electron. The number of electron, the capital N is equal to, we have done it. That should be equal to the N cube, the quantum number cube, times the volume of the material divided by the 24 pi square. This is the number of electron inside the metal. We know from these expressions what is the value for the n, the first expression. Substitute here. So you will get the number of electron n is equal to V divided by 24 pi square. My n cube is nothing but 2m e L square divided by 24 pi square. This is my n, 1 by 2. This is my n. You can just cube this value because it's n cube. So you can cube this value, that is 3 by 2. This many number of electron is allowed inside the metal box. That means which metal if you are taking, that metal length, if you know the energy for the electron, you know, then volume of the metal, you know, then you can simply do the calculation for the volume, how many electron inside the metal. Suppose if you want to calculate up to the Fermi energy, you can just simply do what is the up to the Fermi energy, how many electrons are available. Suppose if you are taking the copper, that value approximately is equal to 10 power 24 electron per meter cube. So now our aim is we want to calculate the density of states in the particular energy interval. So how you can compute the density of states? Already we know that the expressions, so we can complete within this slide. The density of states we can call simply DOF. The density of states you can simply call G of E. The density of states simply equal to the number of electron, that Dn, in the particular energy interval d. So this is simple because we know that n, just you can need to take the derivative with respect to the e. You can tell all the other quantities are simply constants. That means the volume of the metal is constant, 24 pi square, then length, then everything is constant except the energy. So you can call those constants simply C. That is a constant times the energy E 3 by 2. So this is the number of electron. You need to take the derivative with respect to E, this value. That means d by dE of n. So so if you are taking the derivative of constant, it's simply constants. It will come out. So you can take the pull out the constant. You can't take the derivative. This is simply constant. You can take it out. If you're taking the derivative with respect to e power 3 by 2, it will give like 3 by 2 times e power 3 by 2 minus 1. It's off. That means the density of states, the g of e. This is another constant. The c is one constant. 3 by 2 is another constant. You can call the new constant is c prime is e power of. So my density of states is proportional to the square root of the energy. That means the allowed energy of the electron. That means it will vary, the density of vary with respect to the energy as square root of the energy. So now we need to plot this one. How you can plot means we have the expression, the density of states for the expression, the g of e is equal to some constant times e power of square root function of energy. So draw the y-axis is the density of states axis G of E. Then the x-axis is the energy, the allowed energy of the electron E. It will vary as a square root function, so it will go like that. But up to what energy is allowed, that there is a certain maximum energy that is called, we can call that is a Fermi energy. Up to Fermi energy, that is a maximum unload energy for the electron inside the metal. Up to Fermi energy, you can fill up the electron. That means up to this energy value, the states are, all the states are occupied. So this is the electron density, the allowed density of the states in the bulk material. But this is at absolute zero. These are the states are allowed at absolute zero Kelvin. That means T equal to 0 Kelvin. Suppose if you are increasing your temperature, what would happen? Suppose at any finite temperature or room temperature, this electron, the inside the electron, it can't have much sufficient energy to cross the Fermi energy. But at the Fermi surface, that means at the top of the energy states, this electron can cross this energy level. That means your Fermi energy will vary like that. You can choose different color. So at any finite temperature, this electron cannot penetrate, but only the at the Fermi surface, the maximum allowed energy of the electron can gain the energy, then it can occupy the some higher energy states. That means there is a few probability of the electron occupy this above the Fermi energy. But which electron will occupy means only 0 Kelvin, what are the electron sitting near the Fermi surface, those electron can occupy near the Fermi energy. There is a here there is a empty states. This is a empty. This is occupied states. If you are keep on increasing the temperature, then it will vary. This is the curve for at room temperature at any finite temperature. You can call this curve at room temperature of with energy kBT energy. This is thermal energy. So So now we will look at some of the metal, how many electrons are allowed at a room temperature. So look at this table. The metal sodium, the density of the electron is 2.50 into 10 power 8, 28 per meter cube. The Fermi energy, the maximum Fermi energy is 3.1 electron volt. Similarly, the silver also, it is having the number of density of states of electron 5.76, but the maximum Fermi energy 5.5 In copper it is 8.50. The maximum allowed Fermi energy is 7 electron volt at 0 Kelvin. If I look at the table, as the number density is keep on increasing, the Fermi energy, the maximum allowed energy also getting increased. Why means if the number of electron is occupying from the lower energy states to higher energy states, so if the density will be large, then the allowed energy also will be large, then the maximum energy will be large. That means if you are look at the aluminum, the density per meter cube is 18.10 into 10 power 28 per meter cube. The Fermi energy is 11 electron volt. So this is our end of the lectures. I think hopefully you can understand some points from our first lectures, because already we have discussed with these topics in the first unit, then density of states of the electron in the metals. So hopefully it will be small recap for you. So we will see in the next class with a new topic. See you people.